But she taught middle schoolers with behavior problems.
I see.
So it was very challenging. I couldn't have done it for one day.
I hope you teach my boys. I have 3 boys.
Oh, wow.
The first one just joined U of A. So now he is university student.
Oh, good.
And
But-
what's he studying?
He said he will try optics.
Oh, really?
What I am doing. Wow, we will see how it goes.
Were you singing behind me? You have a very good voice. Were you in church?
No,
Okay, with
no.
someone else.
But I hope I sing good. Very nice to meet you. I am the speaker today. Yeah. Oh, yes. Thank you. But very nice to meet you because my 3 boys are all attended the schools here in Tucson, USA.
Yeah.
My 3rd boy is still 9 years old.
So almost 10 years difference between the oldest and the
Yes, 9 years difference. 18, 17, and 9.
youngest. Oh, wow.
I cannot tell how quickly time went by. Unbelievable.
Morning, Tom. Chuck. I'm afraid if Janet had something like that, she might wreck
I've been sick.
This is a beautiful community and also place. The stainless glass is absolutely standing out. Wow.
But I have to tell you, you have no chance of getting the best talk of the year. Because in the spring, we had the group that raises guide dog puppies for the blind. And they brought 10
Actual dogs?
10 golden retrievers that range from little puppies to full-size dogs at the end of their training.
I should
It
bring
was-
my ginger,
it was-
Italian
it was so
Greyhound.
cute.
That's amazing. Wow. So your church actually has this kind of, how I can say, inviting someone, give a talk. We don't have.
So one of our member families has been raising puppies for 25 years maybe. So they know the people in this club, which does the. So it's all who you know. You know, I know some telescope people.
Oh yes, you do know some telescope people, I can
So
tell.
our theme is sometimes medical and sometimes
Oh.
it's about a mission project, but it's often related to telescopes or astronomy.
That's amazing.
All right, let's
Thank you.
get started. Good afternoon, folks. It is my great pleasure to introduce my friend and colleague, Dr. Daewook Kim. Everything is written here on the screen. He's an elder at the Korean Presbyterian Church. And he's a professor of optical sciences and astronomy at the University of Arizona. That gives you a hint about how I might know him. And today he's going to talk to us about Journey to the Genesis of the Cosmos with Extreme Telescopes. So I've so often told you about, a large binocular telescope. That's just a routine old telescope. But I was going to tell you about the really new extreme stuff. Daewook.
Thank you, John. Good afternoon, everyone. It is my immense pleasure and happiness to meet all these amazing people here at Trinity Presbyterian Church members. Genesis, or start of something, is always beautiful, profound, and important. I just heard from John that this church is more than 100 years old and the very first Presbyterian church in Tucson. We need to start something one day, and then the future generations will pick it up from there. So it's my happiness and pleasure to be here. As you heard, my name is Daewook Kim. I am from South Korea. 20 years ago, whether you believe it or not, I was very cute. I was a cute little boy. I came to Tucson with my wife, just married, and then now I have 3 boys, 19, 18, and 9 years old. Again, we start one day, time goes, beautiful things happen from there. That's power of love also. 20 years ago, I was very curious about the Genesis, like universe. And I was thinking, this universe is amazing, and I want to know how it started. People talked about Big Bang. Big Bang. The universe began with a Big Bang. More than 13 billion years ago. And I was curious, well, how do you know if that was real, or how can you study about it? I was very curious. And then I heard astronomers can time travel. That's when I found this is it. I want to study astronomy. As a matter of fact, you can do time travel. How you do? Go outside, look up, and look at our own star. The only star in solar system, sun, right up there. Look at it. Take a photo of it. Do you think you see the sun as it is now? No, we never. We see the sun as it was about 9 or 9 minutes ago. We never see sun as it is. Impossible. Nothing is faster than light. Sound or nothing else. Nothing is faster than light, meaning we never see sun as it is. We always see it as it was. This is profound, because what that means, you are not looking at me as I am now. You are looking at me younger version. Light is not that fast. It's about 1 foot per nanosecond. So 1 nanosecond, 2 nanosecond, 3 nanosecond. You see me about 10 nanoseconds younger. Where is Pastor Matt? Yeah, if you, oh, I love you. You see me really cute and young. My wife is home. That's why she sees me very young version. If you see something far away, you see the past of it. This is incredible, because what that means, if you have a good eye, good camera, like the Large Binocular Telescope John pioneered, amazing telescope, or James Webb Space Telescope, they can take a photo of something far away because it's a good eye, basically. How far away? Well, what about if we take a photo of something 13 billion light years away from us. Why not? We take a photo of the sun only 9 light minutes away. At the speed of light, only 9 minutes away. If you take a photo of 13 billion light years away from us, this is the photo of the baby universe, when this beautiful universe was created. So we are looking at the beginning of the universe. We can be grateful for this wonderful cosmos, and we can enjoy this blue planet in solar system. But that's how we study the genesis of the universe. We are not just guessing. We are not just doing some computer simulations. We can actually look at the universe as it was more than 13 billion years ago. This is cool. Well, one more challenge. If something is far away, what happens is you see me smaller and smaller and smaller. Right? I am getting smaller. That's a problem. In order to see something very small, so far away, you need a good resolution or good resolving power. Black hole, my favorite thing. U of A has an incredible scientist joined this project, Event Horizon Telescope project. And they took the photo of a black hole. How? Well, scientists knew there must be a black hole because they looked at it for years and things were orbiting around center. Nothing. Black. They knew there must be something heavy there. They couldn't resolve it because they did a calculation and they found you need a camera size of the Earth. Then it can resolve black hole, the donut. So how you build a telescope size of the Earth? Even John cannot do it. So here we go. As you see in this video, in order to take a photo of the donut so small, people couldn't take this photo. This is not computer graphic, by the way. The last image is actual image of the black hole. So how you get that? Because this is so small. Well, Tucson has a radio telescope, the camera. But we also have a few more around the Earth. We even have one in South Pole, right here at the bottom. My team just designed an instrument for that telescope. We built it, we put it together, it's working now. The student is about to graduate, PhD. By connecting the telescope, one in Tucson, one in South Pole, another one in Europe, and we connected it. By connecting them, you can make them as a single camera. That's how we did it. And now, if you connect them, now you can claim, my camera is the size of the Earth. That's how we did it. So now you can tell we need a big camera, because big camera means you can take a photo of the genesis or a photo of something far away and small, because it can collect a lot of light. Also, it can see something small. That's it. So now, human are working on next one. One of the very exciting project is Giant Magellan Telescope. It is using 7 segments. Each one is the largest ever made by mankind. It's 8.4 meters in diameter, about the size of this room. We spent 6 years to make one. This is exactly what U of A and the people at U of A, amazing people like Roger Angel, John was one of the pioneers, started it, but also Buddy Martin, many people who educated me started it more than 30 years ago. And now we are dreaming, let's make 7 of those mirrors, put them together, 24 meters in diameter telescope, far bigger than this room. So that's the dream I have been working on this project past more than 10 years. I was single. Now I have 3 boys, all grown up, and it is still going on. So wait maybe another 5 years or 10 years. You will see the largest telescope looking at the universe. We also do radio. You just heard taking the image of the black hole, radio telescope. Let's build many of them, combine them, taking a beautiful photo. Because after all, visible light is good. We see visible, human. Cats may see more. Bat may see more. This universe is full of beautiful electromagnetic wave. That's when light was created. So we have this beautiful electromagnetic spectrum and radio telescope, building hundreds of very large radio telescope. Using them together, we can even see the universe in radio wavelengths. My son likes to cook because I was a cook in the army. 2.5 years I served in the army and I was a cook. I cooked for usually 500 people, sometimes 1,000. My hobby is cooking. Even these days, I cook every day. When my boys have a difficult time at school, let's say, they was not quiet enough during the class, let's say, then they are a little bit depressed. They came to me, Daddy, can you cook pasta? I'm very happy. They love to cook and serve others.
Pasta, not kimchi?
Kimchi also, but kimchi is not easy. Kimchi is not easy for 9-year-old boy. Recently, Jace came to me, Daddy, can I cook pasta? Mom was a little bit harsh to me, but it was my fault. So I said, sure. Let me show you, let me tell you how you make good pasta. He told me, no, Daddy, that's fine. I can ask ChatGPT. And he did. And he got a very good recipe. Unbelievable. Big data. These days, big data machine learning is coming. That's great because he can do more as long as we use it wisely in a good way. In order to educate something, even machine or our children, we need good material. Education is all about we have a good material. Same. For astronomy, now we want to create big data, meaning a lot of information about the universe. So we can understand the beauty of the universe with more data. Big data astronomy is starting. So how we scale it? Well, that reminds me, when I was little and cute, John remembers me when I was very cute, I hope. This is the video I took. This is 8.4 meters in diameter under the University of Arizona football stadium. We have a good football team, yes. And we have mirror lab under the football stadium. This telescope was so special. Oh, I loved it, and I am very happy I was a part of the team. Look at it carefully. There's a one line here dividing the mirror into 2 sections, outer section, inner section, because it has 2 mirrors, M1, M3, primary mirror, tertiary mirror. Why? Because this is the honeycomb mirror, the largest optic ever made, but this one is special because it's a 2 optical surface on a single substrate. Light hits first, going up, that's secondary, coming down one more time. Unlike normal telescope, it has tertiary mirror and light goes up, like Trinity, right? So perfect to be here. 3 mirrors. It allows you to correct aberration. Something is in my eye also, in your eyes also. Aberration limits how sharp we can image things, and 3 can correct those aberrations for wide field of view. So I can see you sharp and focused, but also I see people here sharp and focused. That's what this telescope enables. I was a student, so I had to do some good research. So we thought about, why we make mirror one surface at a time? Usually that's what you do. When you cook a pasta, you do one at a time. But skilled, or at least army cook, who needs to cook very fast, you cook 2 things at the same time using both hands. Here is the example. I was thinking, let's use 2 fabrication tools at the same time. Maybe starting on one side, moving out together, or maybe both ends moving in together. So what we are good at U of A, simulations. We did a simulation study. Do you see? 2 tools are moving in. They are continuously fabricating the optic so that when the mirror has some error, high and low, that we want to remove, 2 tools were moving together and creating a nice final surface. So this is the simulation and research I did back then. And now, as you know, I graduated. So this was a good work. But U of A, we are doers. University of Arizona, we are doers. I think that's the best part of U of A. We are full of people saying, let's do it. So we built it, and as you see in this photo, another photo that I took, 2 tools are working at the same time on the optic. What a beautiful photo. The tool behind, that's what the Roger Angel and John and Buddy Martin, all those people at the Mirror Lab started. It's a robotic tool, changing the shape of the tool depending on where you go. Let me tell you why. Let's say I gave you a pizza dough, and ask you, could you make this pizza dough into a baseball? Sphere. How are you going to do it? You bend it, or you can close your eye, put it on a flat table. With your hands, you just roll it. If you roll it long enough, you have sphere. Because sphere is same everywhere. Right? What if I ask you, pizza dough, could you make it into American football?
That would be tough.
It's tough. How you do it? Depending on where you are rolling, you change the shape of your hand. That's what that tool is. Genius. We call it stressed lab. And I had to do something new, right? So this tool was non-Newtonian or silly putty lab. Literally, I ordered a boxes of silly putty, put the silly putty in this black balloon. So it's a silly putty balloon. It has a lot of silly putty in it. When I ordered it, the staff member asked me, Daewook, I know you have 3 boys. You cannot buy toys for your son. And I said, no, this is for my research. I have a publication. It has slippery in the publication. So I am well covered. So we did that. 2015, 10 years ago, the team at U of A completed it. As you see here on the left, that's the final shape of the mirror. Looks somewhat up and down, right? But trust me, this is such an incredibly good optical surface within our target. If this mirror is the size of the United States, the tallest and lowest error on the United States is less than coin, tall coin dip. Can you imagine? You make United States flat. You may have Rocky Mountain and Grand Canyon because you are not a god, okay? But Grand Canyon and Rocky Mountain should be coin, tall and deep. That's what we did. So 6 years later, we made it. People began to assemble in Chile, 2015. And this year, I was on a business trip out of country, woke up early in the morning because 10 years of waiting. Now, this telescope is running this April. It's a beautiful. Sometimes time is what we need, and I was very happy. What we did here at U of A, 10 years ago, we completed it. Bye-bye, our boy and girl. And this April, it is now up and running. I am immensely happy. Now, let's go to the space. Because after all, God didn't just create Earth. God gave us this incredibly beautiful cosmos, right? It's far more than Earth. So why not going to the space? James Webb is doing great and wonderful. U of A, Marsha Rickey and George Rickey, they are two incredible senior professors at U of A, and they are the PI, co-PI of incredible instruments of this telescope. So U of A is doing a lot for the James Webb Space Telescope. It's very unique because they are using hexagonal mirror, not circle. And they are putting 18 hexagonal mirrors together to create 6.5 meters total. So it's about half of this area. That's the size of the James Webb Space Telescope. Why? Back then, when they started it, rockets were small. It didn't fit. 6.5 meters in diameter didn't fit in a rocket. They had to cut it into segments, they fold it, and then they launch. In space, they unfold it. Smart, great. And me, a little boy, cute boy, working at the mirror lab under the football stadium. Every day you see, ooh, look at these big mirrors. I was happy, but at the same time, I was always like, I envy people at NASA, JPL, MIT Lincoln Lab. They can talk about, we're gonna send our thing to the space. I was a little bit jealousy, right? Because our big mirror is too big. They don't fit. We cannot send it to the space. However, God always gives something great to the people who can wait, right? As you see, now, many rockets are coming. This is SpaceX Starship, currently being developed. But it's not just US, of course, right? Many people in the world will continue to develop bigger and better rockets. Everything looks about the same on screen. That's why our children must go to the real world, camping, see the nature, feel Grand Canyon, right? Mountain Lemon, they must go. Because if you see this thing real, you will see this is not like previous rockets. Because this rocket is big enough that it can fit James Webb Space Telescope without folding. So if James Webb people had this rocket back then, they don't have to make it segmented. 6.5, you just drop into this rocket. Now, I am space kid, right? I can say, Daewook, I can go to space. So the team designed a telescope. Do you see here, M1, that's the primary mirror. M2, M3, right? Trinity, you remember this? 3 mirror, wide field of view. It fits in the rocket, not segmented, single piece of glass, drop in. So we designed it, we published it. Some students are also graduating with this work. What a beautiful world. So sounds like we are happy and all set. Bigger rocket, good design, let's build it. As soon as we have here now, astrophysicists say, no, wait a second, we need more now, right? Can we make many of them? Not one. Now, we have a bigger rocket, you said. Can you have 5 of them, 10 of them? How we do it? Well, first, we need something you can make easy and fast. Because if you want to make many of them, you need to make them not only economical, but also fast. Because if you have to wait 500 years, are you going to? Maybe not. So we came up with this idea using holographic lens. So not like mirror, but look at this. It's a very thin holographic lens. One side hologram, the other side is like lighthouse bulb, if you go there, that side. By putting them together, this thing acts like a lens. But even if you make this lens 8 meters in size, the lens doesn't getting thicker. It stays thin. We made a prototype here. Do you see the rainbow? That means it has holographic pattern on it. Lens, the biggest problem is it creates rainbow actually. That's why people love mirror. Mirror doesn't have rainbow, lens, rainbow. However, how we create this rainbow issue? Because when you take a photo, you don't want to see rainbow, right? You want to see as it is. So we are putting those two surfaces canceling rainbow each other. One surface creating rainbow in this direction, the other one the other direction. They cancel. That's what this is. So the photo on the figure on the left side is actually the figure in the patent. Pretty cool. And then, all right, let's make them quick and fast. How you can make something quick and fast? Molding. Molding. We want to mold something. Glass molding was the idea. Let's put a glass chunk, create a mold, you mold, then you can make many quick and fast. So we cut them in this way, because then if you make one quickly, you make many of them, fuse them, you can get something big. We did a lot of simulation because no one ever molded big, like 8 meters in diameter, glass holograms. So this was very challenging, but we did a lot of simulation, and after 3-4 years of suffering, we were able to mold first of its kind. So this was the very first one This one is about the size of my hand. It took more than 4 years to get here. We were incredibly happy, and now, of course, as I promised, you can make many of them. Here is a one version about this big size. It's still smaller than the Costco pizza. Soon we will go beyond Costco. And then the team took it out to the night sky, and we are doing some early phase experiment. This is small, right? However, the vision is we want to make it 8 meters and beyond. Eventually, this will be a big holographic lens.
Daewook, what does holographic mean?
Holographic means this. So hologram is basically you can not only control brightness of something, but also direction of it. Let's see it in this way. When you see a photo, not hologram, what happened? There is a dark and bright, dark and bright. Forget about color for now. Color is something else, right? So forget about color, just grayscale photo, black and white photo. You see a photo, dark, bright, so you see someone's face. Doesn't matter where you are looking at it. It's the same bright change. If you make same thing using hologram, depending on where you are looking at it, you will see different thing. Why? Because hologram can not only change the brightness, but also direction of how light propagates. So hologram means not only brightness, but also direction of the light.
Does that mean it gives it a three-dimensional?
It gives you three-dimensional.
Oh,
Yes, because three-dimensional means it's not just 2D brightness distribution. Depending on the angle or direction, you see different information.
Okay.
We are using such a lens here. As you saw, we launch many of them, and we deploy. You remember, people say, we need many of them. Here you go. So we have many of these. There is a great people and team at U of A, Daniel Apai, Tom Milster, myself. We are working on this thing now more than 4 years. And one day, this may happen. And the goal of this is looking at the space and see other planets. Like Earth, we want to see other beautiful blue planets in the universe. I have one more interesting story I want to tell. Now, I said, all right, now all of you are happy. No. Some people say, I want to even bigger now. I want Costco pizza. All right. So, not many, right? It's a different problem. Not many of them, they say, we want bigger. Here, radio telescope. Like Event Horizon Telescope, you remember, right? Size of the Earth. That's what they are talking about. This telescope, the left side is the primary mirror, the first mirror, collecting the light. This one, 19 meters. Oh, this room is too small. It's way bigger than this. 19 meters in diameter. How you can, that doesn't fit in the rocket. Even Starship, too small. Doesn't fit. How come 19? Any ideas?
Frequency.
Some magic?
Frequency.
Frequency. Oh,
That's what you're looking at.
right. It's because we are looking at the wavelengths different than visible. Radio frequency, we need a bigger dish. Because it's a longer wavelengths, you need a larger aperture to get the same resolution. So for that reason, we want to say, let's fold it. because you need such a big, big, big telescope. As you see on the right bottom, we fold it, pack it, and then you launch up in space, you open, deploy, and inflate. So this is a balloon. It's a balloon, party balloon. You can go to Fry's and get one Mickey Mouse balloon for your children, granddaughter. Yep, it's a balloon. This is how it looked like. To the right side, do you see that pancake shape? That's balloon. You may wonder, balloon? Wait a second, I don't get it. Well, imagine a balloon. One side is transparent. The other side, reflective. So it's just like Mickey Mouse balloon, but one side transparent membrane, the other side reflective membrane. That's what light comes in, go through the first transparent layer, and then the back surface focus the beam. And that's where all the M2, M3, now we all know this, right? M2 and M3, but they are small and tiny compared to this one. So we designed it. As a matter of fact, 1996, if you remember, we used to have something called Space Shuttle, NASA. Oh, that was a lovely, lovely thing, right? Space Shuttle took it. Not this one, but back then 14 meters in diameter for radio dish. It's like your satellite TV dish, not taking a photo, but radio communication. If you look at the very top left figure, you see human behind it. The tiny dots, that's human.
Oh my God.
But this is only 14 meters. Now we are talking about way bigger than this, 19 meters in diameter. So that's what we want to do. And here is a video. So they are inflating it. And as you can see, this is possible. Ta-da! Back then, it was only for communication. Antenna, now we want to make it as a imaging mirror, not just for communication.
So is it inflated with air?
Inflated with gas, not air, gas. Different types of gas can be used, and we are investigating what is the best gas to do this in space. This one was not even far in space, right? However, we are working on an investigation defining what is the best gas mixture to do this.
Do you use inert gases?
We want to use a very stable, non-reacting gases. Yes. You just saw the video. We were inflating 1 meter prototype. I am taking the photo. Do you see now? That's image of me taking this photo. Ah, nice. I need my wife here. So we made 1 meter version, inflated it. Now the question is, there is a famous saying, you cannot make anything any better than you can test. I think it's an insightful saying. If you cannot measure something, how you can even make it? Or how you can even say, yes, I get what I want? If you cannot taste it, you cannot cook. If you cannot appreciate something, you cannot even know what is meaningful. It is really important that we have a way to sense something. It's far more than you just do something. There must be a way to sense, measure, evaluate, and be grateful about it. So the founder of our college, Jim Wyant, I was in his classroom. I took his class. He passed away, sadly, a few years ago. but he said this during his classroom. We have to measure it. We have to measure that balloon. How many people measured a balloon? No, right? The Mickey Mouse balloon, birthday party balloon, they don't have to measure it. As long as they look okay, they are happy, right? Now we have to measure this balloon for telescope. So here, Scooby-Doo was actually the inspiration. This is me at Tucson movie theater. And as you see here, if you want to measure something curvy, something weird, if you know your loving dog, I heard there was an incredible talk this year, brought all the golden retrievers here and like, yes, he or she will get the best talk of the year. I get it. But I have at least Scooby-Doo here. If you know your loving dog, how he or she look like, and then if you see the image of your dog through reflection, because you know how your dog look like, you can calculate what was the shape of the mirror. That's the idea. Here, in real world, this is display, like TV. That's where we display Scooby-Doo. Or scientists, boring people, sinusoidal pattern or cosine pattern. Something we know. This is our mirror we want to measure, or balloon we want to measure. What is the shape of it? Here we have a camera looking at how that pattern look like. So easy and simple. And if you do a good job and with great passion, like Isaac Trumper, former graduate student, now he's a Dr. Trumper, he implemented it. He created a magic, colorful Scooby-Doo. This is the pattern. It's a two-dimensional sinusoidal pattern with RGB together. Again, the shape we know, our Scooby-Doo. And there is a camera, FaceTime camera. He actually used his own iPhone. He even made this app. We are even thinking about being a millionaire by selling this app. We are two academic persons, so we didn't go that route. But he literally had an app. I was able to open the app, and this thing popped up. So with that, here, the iPhone. Here, we are measuring something really precise. This is called as a deformable mirror. It's a mirror changing the shape in and out, real time. This is widely used technique for adaptive optics. Deformable mirror, and right now you are looking at the actual measurement using iPhone. So we are changing the shape of the mirror by pushing the mirror surface behind it, and we are measuring microns of shape change. This is what iPhone did, and we measured it down to 20 nanometers of RMS accuracy. Yeah, using iPhone. So we are again dreaming about being a millionaire. Time goes, everything is getting bigger. We all grow. So now we are using iPad Pro. We are using iPad Pro, not iPhone anymore. So bigger Scooby-Doo, bigger camera. We are not using FaceTime camera anymore. Apple's software policy is not that easy. You cannot access the raw data easily. It's just really difficult. So we are not developing app anymore. We are just using iPad Pro as a really good display, Scooby-Doo display. And then we are using our own camera. We made it because we want to put that balloon into big vacuum chamber. So here is the big vacuum chamber. We worked with Northrop Grumman in California. My team went there about a week. This big chamber is actually like space-like environment. It's dark, cold, vacuum, and you put your balloon in it, and we create space-like environment because we want to make sure this balloon works well in space, not on Earth. So we put it in a lot of thermocouplers to measure the temperature in space-like environment, all those things. We closed the vacuum chamber. There is a one window. That window is where we mount the system we just described. iPad Pro and the camera looking through the window. And we made a measurement. We are very happy. This is now showing how the shape of our mirror is changing. What do you want? Nothing changes what you want. On orbit, we have a big 19 meters in diameter, bigger than this whole room. Big balloon inflated. We don't want it change the shape. Frozen forever is what you want. So ideally, everything must be just zero. Same color, everything. No, it is not. It is changing. It is changing the shape. Every 5 minutes, every 4 minutes, it is changing a little bit. But if you look at the scale bar, that's in micron. So 19 meters in diameter is changing only a few microns. Oh, your hair is very thick, right? We are talking about really small. And this was possible, and the team confirmed it. And the last big question, because always we want to be critical. Let's do a critical thinking. What can go wrong? James Webb Space Telescope is a great example. When James Webb Space Telescope was launched, very soon there was a breaking news worldwide. There was a space car accident. What happened? Micrometeorites. Space, there are so many small particles flying really fast in space. So one hit the mirror of the James Webb Space Telescope. You saw 18 hexagonal gold mirror. Well, they knew it. Of course, they already thought about it. So it is totally fine. Looking at here, that was before the accident. This is after the accident. I hope you can see right here, the bottom right corner, there is some bump. That's where the micrometeorite hit the mirror. This one is, by the way, from the NIRCam. NIRCam is the instrument PI'd by Marsha Rickey, I mentioned at our university. So we measured it. Okay. James Webb is fine. What about your balloon? Daewook, you are doomed. Your balloon will pop, and that's end of the story. No. The team, this project is led by Chris Walker, me, Ujuru Takashima. There are a team working on this, and we said, no, it is not. We have to prove it. Let's prove it in a straightforward way because people is not believing us. So when I was there with my team, we went to Joann's. I don't know how many of you know Joann's. We went to Joann and we bought a needle, sewing needle. And I put that needle behind that balloon in this vacuum chamber. And the people there said, Daewook, you are the first one putting a needle from Joanne into our space-like environment chamber. Guess where the needle is now? In my office. In a nice zipper bag. One day, that will make me really a millionaire, maybe. It may end up Smithsonian. Maybe Museum of Science History. So we literally got that needle. We did all the tests. You saw the shape change test. We did all the tests. And then last day, I was in charge of engaging this needle into the balloon. Everyone was like, oh, please. If it pops, that's the end of the story. So as you see here, on the right side, we did it twice. Once and one more time, 2 times a puncture. This was the photo of microscopic photo. After we finished this whole experiment, open up, and then we took a photo. So that's what it was. It was a big hole. Here is the video of our Scooby-Doo, unprocessed. Intentionally, I'm just showing you unprocessed raw image. So we are not doing any Photoshop, any computer graphics. No, no. So this pattern is how funny Scooby-Doo look like now. As you see, popped. If the balloon popped or changed the shape, what will happen? Your funny Scooby-Doo will change the shape or go away. It is not. Even after we popped it, the funny Scooby-Doo is still there. So how come? Because the balloon in space doesn't pop. It's interesting. How come? It's because in space, outside is vacuum. So in order to inflate a balloon, you need a little bit of gas. Little bit of gas. Just that will inflate big balloon. What that means, even if there is a one hole, 19 meters size, far there is a hole. I have only so many molecules, gas molecules in this big balloon. There is a hole, and I will not going to go there. Right? It's far away. Not many gas molecules to escape. Second, it's space. Things are cold. Cold means people are not moving around. In Tucson, we are all moving around, right? Cold, so gas molecules doesn't move around. I'm sitting here, I will not gonna go there. See you next year. So it will eventually deflate. However, very slowly. So how you do this? Well, you just bring small gas tank. And then you refill slowly. So even if you have some holes, the balloon doesn't pop. And by adding gas slowly, maybe 2 years, 3 years, you can maintain the shape of the balloon. Now we are working on 3-meter version of it. This is one of the 3-meter version that we worked on. And we are trying to make this thing bigger and bigger and bigger. So this will let us go through the genesis and the beauty of the universe. We are building these telescopes not because we just need something to do or students need to graduate or they need a job. No. They are good, real reasons, but not the reason. The most important motivation is this cosmos and this universe is amazing, unbelievable. Right now, you are looking at the photo taken by the telescope I mentioned earlier. 1 and 2 mirror surface together. Stress lab and telepathy lab together. This is the actual photo. The first one released, not computer graphics. I waited 10 years personally, but entire team waited it so long. And this image, this camera, one night it creates here 20 terabytes one night. 20 terabytes, we do not have some realistic sense. So let's say it's a Netflix video. If this is a Netflix video, 20 terabytes, you need to watch it 3 years nonstop. So every night you are downloading a Netflix video, you need to watch 3 years nonstop. Every night. That's what this is doing. So please imagine what our next generation, our children, our grandchildren, our great-grandchildren, what they can do with this. They will see more beauty of this world. They will be grateful more. And I believe they will love this world and life more than ever in that way. And that is my very motivation why we are doing this. And at last, I want to say, it's not about me. Today, I said all these things as if it's my story. Well, because you invited me, thank you. But it is not me. So many people started it decades ago. Someone started it. I am one of their product. I'm very happy product. I got good education. I had a good 20 years here in Tucson community. Today I'm meeting you. Many students in the group also worked on this, still working on this, will work on this project so that we do this as a part of this wonderful world. And I am very happy that I was a part of this team. Thank you. That was the end of my technical talk, but I also want to say one person. I personally want to say it's a Moore. So Moore also passed away in 2023, just like Jim Wyant. That year was a sad year for me. Wyant was a great teacher to me. I personally learned from him. But you heard about this Nautilus telescope sending many holographic lenses. That project was initially funded by Gordon Betty Moore Foundation. It took many years. It took way more than we originally thought. However, sometimes people believe in your vision and they continue to support. 2023 was the year right after we finished our first successful glass mold, finally. So his passing was after that. I want to say there are many people I want to thank for what we have done. And today, it was my honor to share it with you all here at the Trinity Presbyterian Church in Tucson.
Thank you.
Thank you.